We are going to start our organic chemistry unit today. There's a couple of sections in here which we may end up with 2 or 3 quizzes based on this. Today we're going to kind of establish what organic substances are. So the first thing we're going to do is define when something is organic. Right now you may think of organic as being food and the way that they grow it and things like that, but technically, according to chemistry, something is organic if it contains carbon and hydrogen. There is one case where it wouldn't have hydrogen, but they don't typically ask about it. So when something has just carbon and hydrogen in it, which are the simplest kinds of organic compounds, we call them hydrocarbons. And we're only going to be talking about hydrocarbons in this unit. And you can see hydrogen and carbon right in there. If they have anything other than carbon and hydrogen, like take for example oxygen, it is still organic, but it's not a hydrocarbon. So some characteristics of hydrocarbons, these are things you're going to have to memorize. They are nonpolar. And I'm talking about the molecule when you're all done. And that kind of makes sense. If you recall, carbon makes 4 bonds like this. So if you have just carbon and hydrogen, they're going to combine together to always look symmetrical. So we could keep going with this chain, and then off of each of these would be hydrogens and so on. But when you're all done, it's still symmetrical, so it's going to be nonpolar. Because it's nonpolar, they are insoluble in water. Water is polar, and like dissolves like. Since they don't dissolve in water, they are non-electrolytes. So when you put them in water, since they don't dissolve, they won't make water conduct. So they are non-electrolytes. In general, organic compounds have very low melting points and boiling points. The bigger they are, the higher the melting and boiling point is, which we discovered earlier in the year in looking at nonpolar substances and their size relative to their melting and boiling points. So the bigger they are, the higher the melting point and boiling point is. And then the last thing, organic reactions are really slow, and we're going to get into that more in the last section, but they're really slow reactions. And hopefully you'll get to see in lab some organic reactions. All right, there are 3 kinds of hydrocarbon chains, and they are alkanes, alkenes, and alkynes. What's really nice is you don't really need to memorize those things because we have table Q. My table Q is really small. I can make it a little bigger for you, but the writing will go over it, so I'm going to keep it about here. So in table Q is listed alkanes, alkenes, and alkynes, and then it has something that says a general formula, where they give you the subscript on carbon to be N and the subscript on hydrogen to be 2N plus 2. And that's true only for alkanes, and then this is the relationship in alkenes, and this is the relationship in alkynes. Notice that N is the number of carbon atoms. So over here, they've given us some examples to kind of refresh your memory if you forget. So this table is really, really nice. This is ethane. And in ethane, as in all alkanes, there are single bonds between the carbons. And in alkene, you have at least 1 double bond between the carbons. And in an alkyne, we have at least 1 triple bond in between the carbons. So table Q is going to be really helpful for you as we're figuring these out. So there's another term that you're going to see a lot, saturated versus unsaturated. When a hydrocarbon is saturated, it has the most hydrogens possible. So I think of it as it's saturated with hydrogen, kind of like when you saturate like a washcloth or something. It's got so much it can't possibly hold any more. The only time that can happen is when you have single bonds between the carbons. That makes it so you can have a lot more hydrogens on it than, say, this is the same number of carbons, but because of the double bond, now we only have 4 hydrogens. So the only types of hydrocarbons that have saturation are alkanes. The other ones are unsaturated because they have at least one double or triple bond in them. All right, moving on to naming. I know you don't want to talk about naming. We did this earlier in the year, but the naming for organic substances is a little different. In organic substances, we have a prefix that you're going to find in table P. So let me pull out table P here. I'm going to make it as big as I can without covering up my writing. And these prefixes are actually based on, I think these are all Greek. They're based on Greek, and they're telling you the number of carbons. So once you've counted your number of carbons, you'll know what prefix to use in your hydrocarbon name. So let's write that down. This is going to give you, we're going to look in table P, and it's going to give you the number of carbons. So you'll have access to table P. You don't have to memorize any of those. So that's really nice. Now, the suffix. The suffix is going to indicate double or single or triple bond that you may have between your carbons. So that actually you're going to get from here. So if it ends in ANE, it's going to have all single bonds. If it's ENE, it has at least one double bond. If it's YNE, it's going to have at least one triple bond. So we're going to get that from table Q. And then this is going to tell you the type of bond between the carbons. Okay. Hopefully I haven't lost you yet, but let's go ahead and try some examples. So I pulled in table P and table Q because we're going to need those. And we're going to go with our first examples as being alkanes. So the alkanes mean they have all single bonds. And you can remind yourself of that by looking in table Q, and you can see the example of the alkane that ends in ANE has single bonds between the carbons. So our first one here, all of these are ending in ANE, so we know that it's going to be single bonds, and then the prefix is going to tell us how many carbons we have. So we're going to have to look in table P to figure that out, and when it starts with meth, that means it has one carbon. So we have one carbon. It would have single bonds between carbons if there were more than one, but we don't have any. Carbon always makes 4 bonds, so we must have hydrogens off of all of those bonds. You're always going to fill in with hydrogens when you have a hydrocarbon. Let's try another one here. We have ethane for the next one. Eth, when we look in table P, means there's 2 carbons. So I'm going to draw 2 carbons. And then because it ends in ANE, that means from table Q that there's single bond between them, like so. Each carbon needs a total of 4 bonds. So right now each carbon has 1, the one between them, and they'll need 3 more bonds in order to make the 4, and those bonds will be with hydrogen, like so. I'll leave myself enough room there. Just like that. So let's try pentane now. Pentane, pent, if we look here, means 5 carbons. 1, 2, 3, 4, 5. It ends in ANE, which indicates that it's an alkane and will have single bonds. Single bonds between each of the carbons. And then each carbon needs to have a total of 4 bonds. So this carbon on the end will get 3 hydrogens, so that it has a total of 4 bonds. But the internal carbons, since they all have 2 bonds, are only going to get 2, so they each have a total of 4. And then our end carbon, or terminal carbon, has 3 again because it only had 1 bond with the adjacent carbon. And that's how you draw them from the name. Now let's look at alkenes. Alkenes are alkenes because they have at least 1 double bond in them. All right, so let's look at our first one. We see we're going to have at least 1 double bond, and it has eth number of carbons. Look at table P. Eth means 2. 1, 2. Looks like we're only going to have 1 bond between the 2 of them, so that's where my double bond is coming in. That's where the ene comes from, looking down here. Okay, and then they need to have a total of 4 bonds. They each right now have 2, so I'm only going to be able to put 2 more bonds on each one. I know these are nonpolar, so I need to make sure that my molecule is symmetrical, and you can do that a couple different ways. You can, which is actually more accurate, draw them out at an angle like this, and that's perfectly acceptable. Or, maybe more likely, you might draw them like this. Any way you do it, you have to draw them symmetrical because we know these are nonpolar. I'm going to draw them at the angle because that's actually more accurate. Like that, and then I'd put my hydrogens on there. Okay, let's look at the next name. We have 2-pentene. Okay, that 2 is kind of freaking me out, so I'm going to take a break on that. And I know my ene means I have a double bond, and pent means I have, according to this table, 5 carbons. So I'm going to draw my 5 carbons. I think I'll need to move this. 1, 2, 3, 4, 5. Now the ene part is telling me I have a double bond. Where am I going to put it? I got lots of choices here. That's actually what this number is telling us. It is the address for where that double bond is. Each of these carbons has a number. This is carbon 1, 2, 3, 4, and 5. Unless I counted from the other end, then this would be carbon 1, 2, 3, 4, and 5. And we'll talk a little more about how you know which end to count from. But since I'm drawing this time, I'm going to start from the left, and my second carbon is this one, so I'm going to put that bond between the second and the third carbon. The rest of them are single bonds, since they didn't tell me about more than 1 double bond. And now I need to make sure each of my carbons has a total of 4 bonds. So this first carbon is going to need 3 more, and we'll bond those to hydrogen. My next carbon, though, has 1, 2, 3 bonds on it, so it's only going to get 1 more hydrogen. I'm going to put it down below. And the next one is going to get 1 more, so I'm going to put that one up top, kind of keeping a little bit of symmetry going on here, even though it's above and below. They won't mark off for that. My next carbon has 2, so it will need 2 more. And then my terminal carbon again will get 3. So it has a total of 4. All right, so that might have been a little overwhelming, but we're going to keep plugging away. Alkynes. If we look at our table Q, our alkynes have at least 1 triple bond in them. Okay, so let's start with our first one here. We have propene. Prop, when looking at table P, means that we have 3 carbons. 1, 2, 3. The ine, we said, means that it has at least 1 triple bond. In this case, it doesn't actually matter which one you put it on. When we count our carbons, the carbon that is closest to whatever is interesting in that molecule, in this case the triple bond, becomes carbon number 1. So right now, the way I have this drawn, this would be carbon number 1. But let's say I didn't put it there, and instead, oh, I can't erase it. I'll draw it over here. Instead, what if I drew it here? Well, now this is carbon number 1. So it'd be kind of like I was looking at it from behind my paper. Oh, and I can't erase it, so we'll just do that. All right, so let's finish drawing this. our center carbon here needs one more bond to the next carbon. And it, if you look at it, has a total of 1, 2, 3, 4 bonds. So you are not going to put anything on that one because then you'll have more than 4 bonds, and carbon can't do that. This carbon, however, the first one has 3, so it needs one more. And my terminal carbon at the other end needs 3 more in order to have a total of 4. Move this up a little bit. So this next one, our next example, says 1 Pent-ine. So this is going to be an address for something, but let's look at the pent first. If we recall from table P, pent means 5. So we're going to have 5 carbons. 1, 2, 3, 4, 5. And when we look at the ending to the word here, it tells us we have at least one triple bond. You can always reference table Q to remind yourself of that. Have a triple bond. And the address we were given is actually referring to where that triple bond is. It's on the first carbon. I'm going to count from the left, meaning that my first carbon is right here, and that triple bond is going to be between the first and second carbon. The rest then are single bonds, and then I need to make sure that each of my carbons has a total of 4 bonds. My first carbon right here currently has 1, 2, 3 bonds, so I am going to make up my fourth with an H. It's best if you put it off the end like that so it kind of keeps some symmetry. My next carbon already has 1, 2, 3, 4 bonds. The next one has 2, so it needs 2 more. 1, 2. Next one, same story, need 2 more. 1, 2. And the last one only has 1 bond, so I need to give it 3 hydrogens. And that is what 1 pentine would look like, unless you looked at it from behind your paper, in which case the whole thing would be flipped. And the triple bond would be on the right side of the molecule. So then the question always comes up, what if we had molecules with more than one double or triple bond in it? How would you name that? How would you draw that? So this first one we have here, note that there are 2 addresses, and that's going to give you a clue that you have 2 of something. What that something is indicated at the end of the word here where you have that di. Di actually means 2, just like bi can mean 2, like bicycle. Di can mean 2 as well. And it has 2 ENE. ENE, if you recall, means it has double bond. So what we have here when we dissect it is we have a 5 carbon. When you look at table P, that'll remind you that pent means 5. So we have a 5 carbon chain. So I'm going to draw 1, 2, 3, 4, 5. Maybe you can space yours better than me. And we have on that carbon chain 2 double bonds, and the addresses out front are going to tell us which carbons they're on. They're on the first carbon, number 1, 2, 3, and on the third carbon. The other ones are all single bonds, and then you need to make up the difference with hydrogens. So that first one needs 2 more bonds. This middle one needs just 1. Same thing here. I'm going to make them opposite each other. Same thing here. It's actually kind of how it happens. These are all 3-dimensional structures, by the way. It gets much more complicated at the college level. Just like that. And then it's always good to go back, and what I do is I kind of swirl my pencil around, make sure I'm only cutting through 4 lines, 4 and only 4 lines or 4 bonds, so I didn't mess anything up. Yep, perfect. In fact, when I grade your papers, that's exactly what I do. All right, last one here. Again, we have 2 addresses. Prop means we have a 3 carbon, and there are 2, and ene tells me double bonds. So first I'm going to start by drawing my prop, my 3 carbons, and I have 2 double bonds. They are on the first and the second carbon. And now I need to make my total of 4 bonds. Middle one already has 4, and the end now has 4. Just double check. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And that's as complicated as hydrocarbons are going to get right now.